Hi everybody, and welcome to example 2 on page 73. And this is going to be another example to help us to kind of get to know these left multiplication operators that are going to sort of form the backbone of the work that we do in this chapter 3 summary. Okay, so if we read example 2 together, they'd like us to find bases for the range and the null space of L of A, where A is the matrix shown below. Okay, and they also do some row reduction for us. Okay, so let's start with the problem of finding a basis for the range of L of A. Okay, what's going to be really useful to us here is to go back and remember the observation that we made in example 1. The range of L of A is just the span of the columns of the matrix A. Okay, and we've already found bases for subspaces that have this form long ago in the course. I think way back in section 1.6, we came up with a nice algorithm for finding the basis for a subspace that looks like a span. Okay, in particular, we can do that by just picking out the pivot columns of our matrix A. Okay, so let's start our discussion here by making that observation. So by our observations from example 1, and previous work, we know that we can come up with the basis that we're looking for by identifying the pivot columns of A, and this row reduction that they did for us above is the key to doing that. Let's look at the reduced matrix and circle our pivot positions. Okay, so there's the first non-zero entry in the first row, first non-zero entry in the second row, and then in the third row. Okay, so we've got 3 pivot positions, and the 3 columns of A that correspond to those locations should give us a basis then for what we're interested in here. Okay, so the basis, I'll call it BR, for the basis for the range of L of A, is just going to be the 3 corresponding columns from A. Okay, so let's see, we've got a pivot column. We've got a pivot position in the first column, in the third column, and in the fourth column. So we want to take the first, third, and the fourth columns of A. Okay, so 1, negative 2, 1, 0, 1, negative 1. Okay, and then 2, negative 4, 3. All right, and there's our basis for the range space of L of A. Okay, so it turns out all we have to do basically is to reduce our matrix. Okay, and that's some work. I mean, if you do it by hand, but I mean, it's a pretty straightforward process to come up with that basis. All right, now what about the other part of this question? They'd also like us to find a basis for the null space of L of A. There we have to work a little bit harder to get it. Okay, so let's start by reminding ourselves what the null space is. Okay, and this goes back again to example 1. The null space of this particular linear transformation is the set of all solutions to the system AX equals 0. Okay, we'll start from there. All right, so it's kind of like, I'm gonna clear a little bit of clutter away here. We want to solve a system of equations where our coefficient matrix is A and our right-hand side is 0. So if we were going to do that, we would do the same row reduction that we did above, and we would append a right-hand side that looks like 0, 0, 0. Okay, so imagine solving a system that kind of looks like this, and just for the sake of our discussion, I'm going to give a name to this reduced matrix. I'm going to call it U. So if you hear me later in the problem talk about U, that's what I'm talking about. Okay, so we need to solve this reduced system of equations that we're looking at here. Okay, so I'm going to circle those pivot positions again. First question is, how many free variables do we have? Well, the free variables would correspond to the columns where we don't have a pivot position, and so it looks like the free variables would be x2 and x5 then. Okay, so we'll start from there. So let's let x2 be t and x5 be u. Okay, those are our free variables. Okay, and then we'll look back at our matrix. Okay, I'm going to try to declutter now and then just so that we don't have to look at too much stuff here. Okay, so what I'd like to do is to start with the simplest of the three equations, and that's going to be the last one. Okay, if we read that off, we get a bunch of zeros, and then we get 1x4 minus x5 equals 0 on the right-hand side. Okay, so x4 minus x5 equals 0. Okay, and if we take that and solve it for x4, we get x4 equals x5, but x5, we've given the value of u, looking at the equation above, so x4 is u. Okay, then, move back to the second equation. So if we read that one off, it looks like x3, there's a 0x4 plus 2x5 equals 0. And if we take that and solve it for x3, we're going to get x3 equals minus 2x5, which is negative 2u. Okay, and then finally we get up to the first equation. That looks like, let's see, x1 minus 3x2 plus x5 equals 0. Okay, if we take that and solve it for x1, we're going to get, let's see, x1 is equal to 3x2 minus x5. Okay, and the values of x2 and x5 are the values we assign to the free variables, so we're going to get 3t minus u, it looks like. All right, so we're just following the same process that we use when we solve a system of equations, and notice that we have values for all 5 of our variables. So x2 and x5 are up here, and then x1, x3, and x4 are those 3 numbers that we just found. Okay, so we are in a position now where we can write down our set of solutions. Okay, so the null space of L of A then would be the set of all vectors, x1, x2, x3, x4, x5. We'll just write in the 3 variables that we got. So x1 is 3t minus u, x2 is t, x3 is negative 2u, and just working our way across, okay, where t and u can be anything. All right, and now recall, this is a calculation that we've done many times earlier in the course. We can pull this apart into its 2 components, okay, t and u, and write it. I'm going to skip a few steps here as the span of 3, 1, 0, 0, 0. So the 3 and the 1 are the numbers that go with the t's in this tuple that we've got above. And let's see, the second one would be the coefficients on the u's, negative 1, 0, negative 2, 1, and 1. Okay, and again, I'm skipping some steps here because this is a calculation that we've done so often. I'm trusting that you can maybe look back at some of the work that we did earlier and fill in the gaps here. Okay, so we've written the null space as the span of 2 vectors here, and that gives us, I claim, a basis that we can write down, which implies that the basis for the null space of L of A looks like those 2 vectors that we wrote down. Okay, so basis for the null space of L of A. All right, now, I did gloss over a little detail here. Okay, how do we know that this is really a basis for n of L of A? What are the 2 properties that a basis has to have? Well, it has to span. Okay, we do know that because of the way that we wrote the null space of L of A, but what was the other property? Linear independence. How do we know that this is a linear independent set? Okay, well, you could check that directly, but there's another way to check it, okay, which I'd like to show you here. Okay, so why does this work to give us a basis? All right, well, we make a couple of observations here. First of which is the system AX equals 0 and UX equals 0. Remember, U was just our name for the reduced matrix above. Have the same solution set. Okay, we've kind of been assuming this all along, okay, that in the course that when you solve a system of equations, you can reduce the matrix. Okay, but there is a theorem in this chapter that tells us that we can do that. I'm just going to mention it. This is the corollary to Theorem 3.13. We may talk about that a little bit later in the section here. Okay, so that's one fact that we're using to make this work. Okay, and then the dimension theorem is the other big piece that allows us to kind of pull the pieces together here. And in particular, it's going to be the dimension theorem applied to this left multiplication operator. Okay, and left multiplication by A, if you look at the size of our matrix, it's a 3 by 5 matrix. So if you think about it, you would need to plug in a vector that looks like a 5 tuple because 5 matches the number of columns in our matrix. And what's going to come out is a matrix in R3, okay, since 3 is the number of rows in our matrix. What does the dimension theorem say about that mapping? Well, if we rearrange the equation, and it tells us that the dimension of the null space of A is equal to the dimension of the domain, R5, minus the rank of LA. Okay, but we know what those two numbers are. The dimension of R5 is 5, and the rank of LA, that's just the number of vectors in this basis up here that we found, 3. Okay, so we're going to get 5 minus 3. What do we get if we do that? We get 2. And notice that that 2 matches the number of vectors in what we claimed was a basis for the null space. Okay, so to put it all together then, we could say the following. Therefore, since the 2 vectors in beta n span the null space of L of A, that we already know from our calculation above, they must also be a basis. Okay, that goes way back to dimension fact number 3 earlier in the course. Okay, so let's pull it all together. Okay, this is a specific example, but we can make a couple of general observations that are going to help us from here on out in this chapter summary. Okay, so the first thing that we might notice is that the rank of L of A is the number of pivot positions in A. Okay, notice that if you go back up to our matrix, we had 3 pivot positions, and that just happened to match the number of vectors, okay, in our basis for the range of L of A. And then what about the nullity? Well, the nullity of L of A will always turn out to be the number of free variables. Okay, because if you look at the basis that we got, okay, for the null space, there were 2 vectors, and that just happened to match the number of free variables. We had 2 of them, x2 and x5. Okay, and these 2 facts, you could go through the same analysis that we just went through above for any left multiplication operator and come to these conclusions. We'll feel free to use these 2 facts in the rest of this chapter summary.